We ready? So who's happy that Germany won? Who's sad? Who don't care because USA wasn't in it? You're like, I don't care. Didn't care even if USA wasn't in it. All right. True. All right. So we're still on renal physiology, and we're going to be on there for a little bit of time now. Okay? So we're going to, over the next couple lectures, talk about the whole process of urine formation. So much good stuff. There's a number of steps needed. Eventually, what ends up in the urine is what happens as a result of filtration, which is what we're going to talk about today, is filtration. We'll talk about the processes of secretion and reabsorption next time. So we're going to do a little overview first, a little anatomy, because it's kind of important that you know the basic anatomy of the kidney, because when we talk about certain events or processes, you're like, oh, that's where we are. So you know where we are when we do it. We'll talk about kind of the setup, how the blood vessels are set up, because it's going to be important that they're set up a certain way so we can have the filtration that we need. And then we're going to look at what things can influence filtration. And we get to do a flashback from Physio 1. Ooh. Do you remember the Starling's forces? Little capillary hydrostatic pressures and osmotic pressures. We get to bring them back, but we're going to apply them to what's going on in the kidney. We'll do it in regards to the glomerulus. And then later, when we do the whole process of reabsorption along the nephron tubule, we'll have to talk about the peritubular capillaries. So we got to make sure in those capillaries, it's all about the reabsorption. In the glomerulus, it's all about the filtration. So those are the things that we're going to be doing for the next couple days. Okay? So before we do it, let's kind of overview some of the many, many functions of the kidneys. Some of what we have talked about in the past. Some of what we will be talking about. Wasn't quick enough. Okay, blood pressure regulation. Did we talk about that in the past? The role of the kidneys? So long-term control of blood pressure, about changing urine volumes, all that good stuff. Short-term, it could be doing things about when we talk about renin. Remember the renin-angiotensin-aldosterone system? Kind of? Familiar? We'll talk about it again if I have to. And I will at some point. Okay? We'll talk about, have a lecture on the whole influence of the kidneys in regulating your water balance. We mentioned it a little bit last time. So we said it's all about maintaining water balance, and so the kidneys are real important in that. We'll talk about a whole lecture on that. We have a lecture on electrolyte balance. We have a whole lecture on acid-base balance. Okay? Blood cell production is the only time I'm going to talk about it right now. What is the role of the kidneys in red blood cell production? Are the red blood cells produced in the kidneys? It's like, no. It's like, what is it? How are they involved in production of red blood cells? They're somehow involved in it. They produce erythropoietin, which is a hormone that stimulates red blood cell production. So the erythropoietin is actually produced by certain structures in the kidneys, and it would increase red blood cell production. Okay? It's involved in, we talked about this when we did the endocrine system, it's involved in metabolism of a lot of hormones, either inactivating, getting it ready for getting rid of, or it gets rid of them themselves. It's involved in formation of a very important, I don't want to say it, hormone, that it's a multi-step process by which you get this active hormone that's involved in calcium balance. Calcitriol. So remember, calcitriol is formed in the kidneys because it converts the, the active form of calcitriol is called 1,25-dihydroxycholecalciferol. That's just too much to say. But it converts the 25-hydroxycholecalciferol to 125. So 1-alpha hydroxylase is in the kidneys. And what hormone kind of stimulates more calcitriol to be made? PTH, parathyroid hormone. Boy, I've been really, PTH, can't even say parathyroid hormone, you gotta say PTH. Actually, it's harder to say, PTH. Parathyroid hormone. Okay, so parathyroid hormone stimulates the production of calcitriol in the kidney, so it does a lot of stuff for you. Gluconeogenesis. Did you know that the kidney is a gluconeogenic organ? Did you know that? What is gluconeogenesis? I hope you know what that means. What does it do? It means it makes some Glucose. What is the major gluconeogenic organ, though? The liver. But the kidneys can also do it. They have the enzymes for it. So they also is a gluconeogenic organ. Some of you are like, oh, I didn't know that. It does, okay? It also definitely, it's all about excretion of waste products. That's why filtration needs to be so high, because it's all about getting rid of waste products. So I want to make sure filtration's adequate primarily to get rid of waste products. But something to realize is when we talk about filtration, filtration is a relatively non-specific process. I'm filtering out the good with the bad. So I want to recapture the good, keep the bad there. So we'll have to talk about processes later about how which we get the good stuff back. But it's all about initially getting the filtration so we can get rid of the waste products. Okay? That's why I said if your kidneys fail, it's not very long before you will die if the kidneys fail because it's job in getting rid of waste products. So if your kidneys are not functioning properly, guess what? You're going to be on dialysis so it can get rid of the waste products. Okay? All right, so let's do a little anatomy. Okay? A little basic gross anatomy. Okay? So, kidneys, little protection by the rib cage, would we agree? Just a little bit, but not complete protection, right? Because those of you played sports or watched some sports, they would say you get a kidney shot because they just got to get right up here. And then some of the sports you can dislodge the kidney if you get hit. Well, you can dislodge. I can dislodge the kidney in a number of different ways, but not me personally. I'm not going to do it. Sorry. Boy, I'm pretty strong. No, I'm not. But does have a little protection. Oh, in your notes it says something about why is the one kidney a little bit lower than the other? It's because we walk around like this, or like this. Because and we pulled it out so you can't see it. Who gets in the way? The liver. Okay, so yeah, that's the reason why. Notice that the kidneys are retroperitoneal, along with the adrenals. So it's behind the peritoneum. Okay? What kind of keeps them in place? What kind of keeps the kidneys there? You got fat, you got fascia, kind of they say it creates like a floating kidney. Believe it or not, that fat's real important. So people who lose weight too quickly, the kidney can fall out of place. And what will happen if the kidney falls out of place, it could kink the ureter. And what would happen if you kink up the ureter? It's not going to be able to go down into the bladder. Things will back up. Pressures can get really high, and it can damage the kidneys. So if they kind of fall out of place. So that sometimes can happen if someone loses weight too fast. That fat is there partly protective, but it's there to kind of keep it in place. So there's a lot of fat around the kidneys. Not, I mean, in your guys' cadavers, do you see a lot of fat around the kidneys? I guess it depends on your cadaver. You're like, oh yeah, probably more. And they said fat around everything else too. Depends on your cadaver. Okay. So let's look at. We're going to section through the little kidney. Why do they call kidney beans kidney beans? Because it's shaped like it. Who came first, the kidney or the kidney bean? I don't know. I know it's philosophical. Do they name our kidneys after the kidney bean or the kidney bean after our kidneys? I don't know. I've thought about that. I don't know who came first, chicken or the egg. Okay? So we're going to section through the kidneys, okay? And let's look at the structures because it's important to kind of know generally where you are. So on the outer portion of the kidneys, we have a pretty picture, and I have one that I drew. So here's the cortex. The renal cortex out here. So I have the little hatch lines. So this is the renal cortex. Is it important that on exams, if I ask you something, blah, 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 and you just put cortex, why would Dr. Kays be upset if you just put cortex? Yeah. I mean, there's cortex where? Adrenal cortex? Renal cortex? Cortex of a lymph node? I mean, it's like, yeah, there's more. So you got to say renal cortex. That's kind of important. As well as renal medulla. So here, the inner part is the renal medulla, where you find the pyramids. See these things that look like pyramids? These are renal pyramids. See the striped appearance to them? What gives them the striped appearance is the fact that what's present there are these ducts that we're going to be looking at that are kind of in those ducts. If something's in there, that's eventually going to be your urine. So they kind of give the little striped appearance. So that's the renal medulla, and these are the pyramids. Now, you'll notice like extensions of the cortex. These are called renal columns, so just like columns. You know, bless you. These little parts here at the ends where it's kind of tipped, that's what refers to the renal papilla. Okay, so these are renal papilla. So what's happening, we're going to be looking at all these things happen in the nephron tubules, and eventually these ducts are going to be draining down in this direction, and it's going to have urine in it, and then it's going to empty right into here. These are your minor calyces. Singular would be calyx with an X. And then it empties into the major calyces, and eventually in the renal pelvis and out through the ureter. You'll notice they have this circle around here. They call it the hilus. I've seen it called hilum, the renal hilus. The ureter is not the only thing located in that region. It's a general region. You have blood vessels coming in and out. You've got lymphatics coming in and out. You've got nerves. So that's just a general area for a lot of things that are going to be located. Now, what's going to be important is out here in the renal cortex, this is where when we look at our nephron tubules, majority of the parts of the nephron tubules are going to be located out here. So when we actually look at just one in isolation, I'll say this is in the cortex. This part may be in the medulla. It all depends on what type of nephrons that we talk about. So the whole process of filtration, though, is going to take place out in the cortex. Because I guess what vessel is out here, that's why filtration must take place out in the cortex. And what would be that vessel? Nope, nephron's not a vessel. What's the vessel? It's a type of capillary. That's fenestrated capillary. That's going to be out here where all that filtration is going to take place. Begins with the letter G. The glomerulus, the glomeruli are going to be out here. So that's where filtration is going to take place. Now the kidney is surrounded by a little capsule. Helps serve a little bit of protection there. So you do have a little layer on the outside. Okay. So on here, have you figured out all these labelings here? So here is the cortex. Here, this is the column. This one is a renal or the minor calyx, major calyx. Actually, no, this one's the column. This one is just representing the medulla region, which more should be here. There's papilla. Here is the hilus, and here's the ureter. Right here, and this is the pelvis, renal pelvis. Okay. So what we're going to be looking at, blood vessels are going to be coming in. The renal artery is going to be coming in here, and the blood vessels are going to branch off and eventually serve parts of the kidney, and we're going to look at what happens to those blood vessels. Then also the veins are actually going to empty out through this region here too. So here's the blood vessels now, so you can see it. 22% of your cardiac output passes through the kidneys each minute. Is that a lot? That's a lot. Why is it so important? It's so high. 22% of your cardiac output every minute. Why is it so important that you have so much blood flow going to the kidneys all the time? It's filtering, yes. It's very important. It's that high. And we're going to talk about how does it get that high. Now notice the vessels. So we got to kind of look through the vessels. So it's almost like an anatomy review, but it's important. Yeah.
Is that per kidney or
Both together. Both together. Yeah, because that would be too much. 44%. It's both kidneys together. It's 22%. Yeah, they should say the kidneys. Yep, both together. So here's your renal artery. Notice it branches into segments. You have about maybe 4 or 5 in each kidney. You've got segmental arteries. And then notice it comes up between the pyramids through the columns. Oh, actually, one thing I didn't mention. This is how the name comes from. This whole thing here, cortex, medulla together, is what we call a renal lobe. L-O-B-E. So this is why this next thing is important. These vessels are called the interlobar arteries. Does that make sense? They call them interlobar. What does inter mean? Between. So it's going between the lobes. Then it kind of makes a little arc. That arc is kind of the fine line between the renal cortex and the renal medulla, and those vessels are called arcuate arteries. Again, you can see just by it makes a little arc. Then you start going up into the cortex. the interlobular. This is where spelling could get you. There's a difference between an interlobar and an interlobular artery. The interlobular arteries extend up into the cortex, and you can't see very well here, so I'm going to move to the next picture. After you have the interlobular, eventually you have the afferent with the A, arterioles, and then you notice over here I have an efferent. And in between, I have the glomerulus. It's pretty much the same vessel, but we just have a filtration unit somewhere in between. The afferent arteriole is the feeder vessel to the glomerulus. The glomerulus are designed, it's a fenestrated capillary, that if you have pressures high enough, you can get filtration there. Whatever didn't get filtered is leaving through the efferent vessel, in this case the efferent arteriole. Now, what you'll notice is these vessels are all arranged in series. Why is it so important to have these vessels arranged in series instead of a parallel circuit? You have a series circulation. So what does it have to do with this series? Do we want filtering? What is it doing, allowing us to be able to have that really good filtration? It's going to allow us to have a higher pressure. It's a higher resistance. So it's a higher, having things set up in series, higher resistance, but that's going to equate to a higher pressure, so I can have the filtration. Plus, you don't really see, oh yeah you do if you look really carefully. Notice the efferent arteriole is a little bit different in diameter than the afferent. So my right hand will be the afferent. Here's the efferent. In between is the glomerulus. So blood's coming here, got the glomerulus. This is a little bit smaller in diameter. It provides a back pressure. So it kind of impedes the flow there. So a little back pressure, what is that going to do? It's going to favor more stuff leaving the glomerulus. So it designed that way is important. And having those afferent and efferent arterioles being different diameter, we're going to use that. I don't want to say we're going to abuse it, but we're going to use it. Because if I change the diameter of those vessels, I'm able to control how much filtration that we get. So if I increase the diameter of the afferent arteriole, what am I doing? I'm going to be able to bring in more blood to the glomerulus. They'll allow me to have more filtration. Or if I decrease the diameter of the efferent to some extent, more back pressure, more filtration. So physiologically, how we mess with filtration is to change the diameters of those vessels. That's how we're mainly going to physiologically regulate filtration, is changing the diameters of those particular vessels. Now, once you leave, the blood leaving the efferent, whatever wasn't filtered, it doesn't stop there. So what happens is, you notice this picture here. Here's the nephron. So here's the glomerulus, right here, the red. This is Bowman's capsule. And what happens, I'm going to draw a little bit better. Here's my Bowman's capsule. And then here's your nephron. So here's the glomerulus here. Efferent here. Well, I just filtered a whole bunch of stuff, and it's coming down here. I filtered glucose and amino acids and electrolytes. Do I want to get rid of all that stuff? If it stays in the nephron tubule, guess what? You're going to get rid of it. So what do I need? I need to recapture it. So do you think I might need some vessels around those nephron tubules that if I reabsorb things, I can take it back into the blood? Well, the efferent arterioles then become the peritubular capillaries. And so you'll have capillaries that wrap themselves around that nephron tubule that allow me to pick up anything that I need to recapture. And then whatever I didn't, then eventually it's going to, it's going to stay in the nephron tubule if I don't reabsorb it. But the blood that's left in those peritubular capillaries eventually is going to empty into the veins. And all the veins are named right after the arteries that we had, or arteria. So they have just the same names. We're just going to eventually take it away. But we do have different types of nephrons in the kidneys. And we have some nephrons with really long loops of Henle, and some that have a little shorter loops of Henle. Have you heard of loops of Henle before from cells and tissues? okay, so it's not the first time you've heard it, but don't worry if you don't, because we're going to look at it again, is some of the nephrons that have very long loops of Henle, those paratubular capillaries, we don't call them paratubular capillaries anymore. We refer to them as vasa recta. But they're going to be specially designed for something, designed a certain way. When we talk about regulation of water balance, that's when they're going to be very important. But we're just going to call those capillaries the vasa recta. Okay, so you got all this blood supply to the nephron. So these are the two different types of nephrons that you'll see. Cortical and juxtamedullary. Wonder why they call them the cortical versus juxtamedullary nephron. Cortical nephrons, that's the most of the nephrons that you have in your kidneys. Where do you see most of the parts of the nephron tubule for the cortical nephrons? What part of the kidney? The cortex. The only part that you may see in the medulla may be just a little bit of the tip of the loop. Most of the rest of it will be in the cortex, except, tip of the loop and part of the ducts as they move down. The juxtamedullary nephrons, what you're going to notice is there's going to be a large amount of this loop of Henle. You notice loop of Henle is a lot longer. Most of this is going to be found in the medulla. So the renal medulla is going to be very important when we talk about regulation of water balance. These type of nephrons are going to be important when we talk about regulation of water balance. So we're not going to talk about it today, but that's where it's going to become important. The blood vessels here, notice they're called the vasa recta. These ones are called peritubular capillaries. How will you remember that name? Peritubular capillaries. How are you going to remember that name? What does peri mean? Around. And it's around what, would you say? Dectopyramid. Okay. Peri doesn't mean dectopyramid. Okay. Actually, if you say peri to me, I think of there's a show on Disney Channel with the platypus. Yeah. I love Perry the platypus. He's so cool. Okay. Phineas and Ferb. That's what it is. Okay. I don't have cable anymore, so I don't get to watch it. So oh yeah, it is true. Netflix. I do have Netflix. Peritubular capillaries. So they go around the tubular. Don't tell me now. I'm going to go watch them now. Peritubular capillaries. So these are capillaries. So this is going to be important. Tell me about a structure of a capillary. Tell me about capillaries. What are they designed for? Exchange, not all exchange, okay? So they have to be pretty thin-walled, right? Okay? So about exchange of arterioles. Do you have exchange in arterioles? No. But in capillaries you do. These peritubular capillaries are going to be specially designed. Everything's going to be set up just right for try to favor reabsorption, get all the good stuff back. What about the glomerulus? What is it? When you say exchange to me, you're like, I'm giving you this in exchange for something else. What about the glomerulus? Does the glomerulus like share? What does the glomerulus do? It's all about filtration. It doesn't take anything in exchange. So it's actually really not a true capillary. It really isn't, because it's all filtration. It doesn't pick up anything. But it's okay. It's really not truly a true capillary. We're just going to filter out some of the stuff from the blood. I'm not picking anything up. Okay, so but they're both designed a certain way. They're both thin wall, but there's difference in their structure a little bit. Remember about the glomerulus. They are fenestrated capillaries, which means what? Or tell me the three types of capillaries that you have. You've got continuous, fenestrated, and sinusoidal. Where do we have the sinusoidal ones? The liver and other places. Fenestrated you see in the kidney. Which of the three are the most permeable? Which of those three are the most permeable? They allow the biggest things to get through. Sinusoidal. Fenestrated are somewhere in between, right? So they let a lot of stuff get out, but what will it not get out unless it's damaged? Proteins, big proteins, and it won't get out blood cells. So if you start seeing blood cells leaking out, large proteins, you probably got some sort of damage to the glomeruli, which is not a good sign. Okay? So, but it does let most stuff out except anything that's bound to a protein, the protein itself, or say large proteins. Small ones can get through, and blood cells. Okay? So let's kind of go through the basic components of the nephron. We're going to do it again next time. We'll be drawing pictures So if you draw pictures, things like you're going to remember things a little bit. I want to introduce you to some of the basic components of the nephron so you kind of know when we talk about certain things. The first part's really not truly part of the nephron, but I'm still going to include it. This here that looks like Pac-Man. It looks like you put a sock on your hand and you went, okay. So what is that supposed to be? That's your, here's my glomerulus, and it's right around it. That's your Bowman's capsule, okay. I'm going to draw in the glomerulus, okay. The two together, anybody remember, or if you learned it with Dr. Perriman, if you took undergrad A&P, you probably learned it, that the two together, what do they refer to as? Bowman's capsule and the glomerulus, what do they refer to it as? Renal corpuscle. So what event takes place in the renal corpuscle? That is all about filtration. That's it, filtration. That really is not part of the nephron in reality, okay? So filtration takes place. Now, once you get the Bowman's capsule, it's going to move on into the nephron, and we have different parts of it. The first part we're going to refer to as what? Because it's closest to the glomerulus. We're going to call it the proximal tubule. Now, some of you heard proximal convoluted tubule, right? Well, it depends. Part of it's the proximal tubule. Some of it's the proximal convoluted tubule. What part's convoluted? The part that's all, yeah, all convoluted, all in the way. So it's okay. I mean, it's like fine line. This part's all coiled up. This one isn't. If you say proximal tubule or proximal convoluted tubule, I know what you mean. I don't care. I'm not that much of a stickler. So if you want to put PCT, you can abbreviate. Or proximal tubule, I'm okay. But here you'll see it's all convoluted. So here's the proximal tubule. Actually, I'm going to extend this down. This looks like there's a line here. I'm going to go down about right here. So this is the proximal tubule. We're going to look at all the stuff that takes place there. It's designed, it's structures specifically designed a way to favor its particular function. Then you'll notice the arrow. This is the order in which everything goes down. So it comes down here. Then you have this part right here. And I'm going to move this down to here. This part right here, what's that thing together referred to as? The loop of Henle. But we have actually three parts of the loop of Henle. This is the descending limb, because it's going down. This descending limb is going down towards the medulla. Remember, if this is a juxtamedullary nephron, this thing is probably going deep down into the medulla. This is the descending limb. Then here, this is the thin ascending limb. Actually, I'm going to change this a little bit, make this a little fatter here, because this is not a really big part of it. Let's just make this a little bit fatter. Thin ascending limb of the loop of Henle. Then you notice it gets thicker, gets fatter. Where it gets a little bit thicker, this is the thick ascending limb of the loop of Henle. I'm just going to put LOH. It's important when you talk about the loop of Henle, you have to distinguish which limb we're talking about. You don't have to say thin descending limb because it's all thin. You have a descending limb of the loop of Henle, but the ascending, you have to distinguish between thick and thin because they do different things. Anybody want to know why one's thicker and one's thinner? The reason why, and actually I'm going to tell you the proximal tubule. It's pretty fat. Remember doing in cells and tissues and you did the sections and you looked at the sections of the kidney and you could see things that were a little fatter, a little bit thinner, and you can try to figure out which was which? The reason comes down to is I have to be fatter to hold more stuff, organelles, things like that, because certain places where you're doing a lot of reabsorption, guess what? You're going to have to produce a lot of transport proteins to have along the membrane to be able to do all this transport. So the places that are thicker, you have more transport proteins. Things that are thinner, They're not. So I'm just going to give you something well ahead of time. Guess what? Guess what happens in this descending limb? Not a heck of a lot. The only thing that happens here is you're going to get movement of water. That's it. You don't have movement of glucose or amino acids or any of that. It's just movement of water. So I don't need to have a thicker membrane to have all these transport proteins in there. There's not a lot of stuff that's going on in the thin descending limb either. But the thicker areas, you just need more room for all those transport proteins that you put in there. Okay? So there's a reason why things are structured the way they are. Now, so far, you get filtration in renal corpuscle. Goes from the glomerulus into Bowman's capsule. Then we do the proximal tubule. Guess where the proximal tubule is located? Cortex or medulla? It's cortex. It's all proximal tubule is completely in the renal cortex. The loop of Henle all depends on which particular type of nephron that we are, but the loop of Henle may be in the medulla or may not, but if it's even a cortical nephron, this is down in the medulla, okay? As we move up, we're going up towards the cortex. Then you'll notice after again, just fine line, this is my drawing, so it was kind of hard. After you have the loop of Henle, we're going to be in the distal tubule, because you're distal, away from the renal glomerulus. Now, we have to make a distinction between early and late, because it's important. The very first part of the distal tubule we call the early distal tubule. And the reason why I'm going to emphasize this is this really is the only thing I care that you know about the early distal tubule, is this is where the macula densa cells are. Have you ever heard in passing a macula densa cell? If not, we're going to talk about it. So right now, just put macula densa cells are here. The macula densa cells are a component of the juxtaglomerular apparatus. So I'm just going to tell you now, my picture is not anatomically correct. It's not structurally correct. Well, I already told you because I've been drawing it, changing. In reality, guess where this part of that nephron tubule is? It's in contact with the afferent and efferent arteriole, because the juxtaglomerular apparatus is part of the macula densa cells and the smooth muscle cells of the arterioles, because that's when we're going to talk about regulation of filtration. That's where it's going to come into play. But right now we just had to give some space. I spread it out. Then after you go early distal tubule, don't you have a little convoluted part here? Is that convoluted right in here? A little coiled up. We have a distal convoluted tubule, but I don't care if you know convoluted versus non-convoluted. But I'm going to start over here saying late distal tubule. Because later, at a later date, we're going to talk about some stuff that takes place in that late distal tubule. That's pretty important. And the cells in the late distal tubule are very similar to cells that you see right here, which would be, cortical collecting tubule, or they can call it the duct. Now this thing's just showing only one thing. This cortical collecting tubule can be collecting things from multiple nephrons. It's collecting fluid from a number of different nephrons. And where is this duct or tubule located? Hence the name. Cortical collecting tubule. It's found in the renal cortex. Okay, so it's collecting fluid from a multiple different nephrons. So we got the late distal tubule emptying stuff in there. So you have those cells there are very similar to the late distal tubule. They're both sensitive to a hormone that we're going to be talking about, and we have talked about in the past. It's involved in sodium and potassium balance. Might be a little something called aldosterone. Okay, so you're like, oh, she goes, oh my God, I got it. Yes. Okay. Yeah, we'll talk. Yeah, so you remember something. When we talk about aldosterone, we'll talk about the specific type of cells that are responsive to aldosterone. There's more than one type of cell in there. One's going to be more important, acid-base balance. That one's going to be one that's responsive. We'll talk about the ones responsive to aldosterone. Then you got cortical collecting duct, and just by its proximity or by where it is, they're going to change the name. Do you ever know the streets? They're going straight, and all of a sudden the name changes. The name of the street. You ever have that? You're like, what the heck did the name change? It's the same street. Same here. You got cortical collecting tubule. Once I start getting in the medulla, guess what they're going to call me? They're going to call me a medullary duct. And it all depends if I'm outer or I'm inner. So just by where I'm localized, they're going to just change my name. So we don't have the cutoff, so you can't see it. But once we start, say, well, definitely down in here, we're going to call this one a medullary duct. Okay? So medullary duct. Now here, the urine is doing its thing, coming here. Guess where these eventually drain into? I've got these things going down through those renal pyramids, giving me the striped appearance. Now at the very end of the renal pyramids, where it kind of makes that little kind of thing, that little rounded shape, what one was that? The renal papilla. Right down there, they're going to call them the papillary ducts. Okay, they just change the name depending on where you are. And where does the urine go from there? Drip, drip, drip into the minor calyx. Then they enter into major calyces, renal pelvis, then out through the hilum is the region. Then when it goes from there, the ureter. And then where does it go? After it goes ureter, it goes to the bladder, and it's filling as we speak. Okay, it's filling as we speak. You're producing urine right now. Okay, you are. I'm going to make you want to pee very soon. Okay, so but everything is set. You're in filling mode. You're not in voiding mode. So you're just filling up, filling up, filling up. It is dripping away. Okay, so whatever was not recaptured throughout this tubule is going to end up in your urine. Okay, and the kidneys are so good. They do things that, hey, if I need to get rid of some extra stuff, I'll get rid of some extra stuff. Oh, got a little too much potassium around? Let's make sure we have more potassium in the urine. If I need to capture more potassium, I will. Water, it can change. Okay, so you can fine-tune everything as long as everything's going correct. So I'm going to get you ready to having to go pee. So I'm getting you set. Ready? Okay. So we're going to talk about the process of urination very shortly. Okay. It has a fancy name for it. So if I section through the ureters, here's a little section through the ureters. Anybody know what type of epithelium that you have lining the ureters as well as the bladder? Transitional. Is transitional example of stratified or simple? Just think about it. What, you know, why would you want more than one layer and only want one layer? One layer is all about just you want things moving across. Do you want urine going from the ureter into your blood or anything like that, moving across? You want it contained? Multiple layers. You don't want the stuff seeping in. Your bladder's filling with urine right now. You don't want that urine going seeping through the walls. So it's stratified. Why they call it transitional? If it was not filled up, the cells kind of look like that. What do they call them? It's stretchy. What was the name of those cells? The dome cells. So then they stretch out. They kind of do this. Okay. So it allows you to be more stretchy, more distensible. Okay. The smooth muscle that lines the ureter and the bladder. Will that be important? So I have urine that just emptied into the ureter. What's it going to do? I have urine, all of a sudden, what it's going to do to the smooth muscle? It's going to stretch it. What will smooth muscle do if you stretch it? Contract. Why would I want it to contract? You want it to move down to empty into the bladder. At a later date, when it's socially acceptable, hopefully we're going to have be able to avoid the bladder, but we're going to talk about this whole process. We're going to talk some reflexes that will be triggered when you start to stretch out the smooth muscle in the bladder, but we're not doing that yet. So moves it off into the bladder, and the bladder's designed where it does have rugae, just like who else had the rugae? Stomach, and they're just folds, unless you have mucosa, or he's coughing, sneezing. I don't know what you're doing. I said bless you. Was that you, Aaron? No? I don't know who was coughing. Oh, it was, okay. I was going to call you, you're going to call your brother's name again. Cass, sorry. I was going to call you Logan again. All right, so they start to, the bladder can stretch, right? The rugae flattens out, okay? Do we want pressures in the bladder to get too high? But if the pressures get high, what's going to happen? Probably going to force things out. It could, okay? But having the Rugae, it can accommodate good fair volume before we have to void. But we'll be talking about that. Now here's the ureters emptying in there. Now you don't really, here see the ureteral openings. This design that you shouldn't have any backflow because I don't want it to go back. Just go in, set it in there. Did you learn about, have you learned in anatomy about the trigon and all that? Okay, so you did that, okay. And you learned about the detrusor muscle, okay? The detrusor muscle is going to be important when we talk about the bladder contracting, okay? So we'll talk about that very shortly. Now this happens to be a bladder from a male. How do I know that? Do the bladders in the males look any different than the girls? Probably not. Yeah, I see a prostate. Okay, so that's how I knew, okay? And the fact that the urethra is so long. Guys, your urethra is much longer than the females, okay? Well, important sphincters. Sphincters are real important when we talk about anything, defecation, urination. You have internal and external urethral sphincters. This is why I marked you wrong on your last exam if you just said external sphincter, because there's more than one external sphincter in your body. There's external urethral and external anal, but they have similarities, which makes it easier if you remembered your urethral or your anal sphincters. Internal urethral sphincter is smooth muscle. External sphincter is skeletal muscle, okay? Just like your other ones. So one's smooth, one's skeletal. So one's involuntary, one is voluntary. They have similar innervations. So the internal sphincter is innervated by the pelvic splanchnic nerves, which are carrying what type of fibers? Parasympathetic fibers. The external urethral sphincter is innervated by the pudendal nerve, okay? Pudendal nerve, which is part of your what system? Somatic. Remember, skeletal muscle is always controlled by the somatic nervous system, okay? Those are going to be very important when we talk about the whole process of micturition. The innervation of the bladder and the neck and the sphincters, so this kind of shows you the innervation. Sympathetics mainly are going to be more involved in more pain type things, so that's not really going to be important when we talk about the whole process of urination, which is called micturition. The parasympathetics and the pudendal coming from the sacrospinal cord. The parasympathetics are going to definitely be important when we talk about the contraction of the bladder. So it innervates the detrusor muscle. It innervates that internal urethral sphincter. The pudendal is going to be innervating the external urethral sphincter. Okay, so to get you ready for your restroom break, if you have to go, you may not have to go. Okay, there's a little reflex called the micturition reflex. So this is completely mediated through the sacrospinal cord. Now, I have to remind you because someone had sent something a little while ago. I'm like, maybe they forgot. You do have 5 segments of your spinal cord. Do we agree? 5 segments of your spinal cord. But where does your spinal cord end? At what level? What vertebral level? About L2. So do you have like, well, the sacrospinal cord, it ends at L2, but don't we have the nerves that come out and then go out that way? So we do have a sacrospinal cord. So we have a defecation center in the sacrospinal cord, and we have a micturition center in the sacrospinal cord. Well, you have the bladder filling up, starts to stretch out, sends sensory impulses to the sacrospinal cord, where it innervates portions of the sacrospinal. There's going to be, they ignore the inner neuron here, so you can barely see it. Then a little reflex comes out, and you have efferent fibers that go to the detrusor muscle and cause it to start to contract. Well, okay, because isn't that might be important when you're trying to like urinate, maybe? Could. So you have this contraction of the detrusor muscle. The external urethral sphincter, though, is going to be contracted. Or actually, no, it's not going to be contracted. This is different from the defecation. If pressures get high enough in the bladder, what's going to do is the internal urethral sphincter is going to be forced open. But the external one, what's going to prevent that stuff from leaking out? The external urethral sphincter needs to be contracted. But thing is, that's going to be relaxed unless you voluntarily contract it. Because you notice how you have to hold it in more when you have to pee than when you have to poo? Remember when you poo that you have to kind of force it out. Here you're like, got to hold it in. Okay, some people have a little better control than others at holding it in. Okay, but there's a lot of higher brain centers that are involved in this whole process of micturition. As it's filling, you're pretty much in storage mode, filling mode. It's protected. These sphincters are usually closed. But at a certain level it gets up, it's like, okay, we need to stimulate this micturition reflex, but simultaneously you have ascending pathways up to higher brain centers. And this only shows one of them. There's insula is involved, there's other brain centers involved in the whole process of micturition. The point where you feel like, I gotta pee, somehow it made its way to the cerebral cortex, like, I gotta pee. Hopefully, you're holding it, right? And then you can find a socially acceptable time to go use the restroom. But do you notice that sometimes you're like, oh, I got to pee, and you're like, I can't go right now, I'm taking an exam, I got to hold it. But then after a while, you don't realize you have to go anymore? Or you feel like you don't have to go until, like, I think it's getting to a threshold level. Well, higher brain centers can send inhibitory information down to try to inhibit what's going on. So higher brain centers can control it. It can facilitate it. It could actually inhibit it. So when you get back from your restroom break, we say, well, what happens if somehow you mess up with the pathways, the ascending or descending pathways? Your ability to control the whole process of urination may be affected. The sacrospinal cord, if that's all intact, you'll have these micturition reflexes where you start to contract the detrusor muscle, the pressures in the bladder get high enough, it's going to force open the sphincters, and you're going to pee. But if all these higher brain centers and the ascending tracts and descending tracts are intact, hopefully you can control it. Isn't it some part of it, the whole process of urination, part of it is learned? Do you agree, those are with children? Okay, don't kids just pee themselves until they're about 2 or 3 or 4, depending? They have to be kind of trying to learn how to control it. So some of this is a learned process. I was just reading a paper yesterday. They're still doing research on the whole process of micturition. It's so complicated. And they're looking at all these different areas in the brain that are involved. Prefrontal cortex, insula, the cerebral cortex. I'm like, oh my gosh, this peeing thing is just too complicated. So I mean, it is. Okay, it is a complicated process. Okay, huh? What? All right. So take a restroom break. When we get back, we're going to talk about some things if things go wrong. Okay. Hopefully, nothing goes wrong with you while you're taking your restroom break, or it's not too late. All right. Let's talk about some abnormalities of micturition. Settle down. All right. So let's see what would happen if some things were damaged in some way, shape, or form, tied in this whole micturition process. So if the sensory fibers are damaged for some reason or other, trauma or some infectious disease of some sort, what would happen is the whole thing that starts these reflexes, these micturition reflexes, you had to have the sensory fibers sending the information to the sacrospinal cord, which then sends the efferent information down to the detrusor muscle. That's not going to be activated. So you'll have no micturition reflexes at all if the sensory fibers are damaged, but you're still producing urine. So you have, think about too, if the sensory fibers are damaged, in no way, shape, and form are you going to ever be aware that you needed to go or need to go, but the detrusor muscle is not going to be contracting anyway, so it's going, the bladder's going to fill and fill and fill, and when the pressure gets high enough, the sphincters are going to be forced open. What they say, they call it overflow incontinence. It just drips out. And then these people, they're not going to be able to like empty their bladder properly. They might have to kind of press down, do something like that. So actually some people who have issues like that can have certain things implanted to try to help stimulate the voiding the bladder. So they call it overflow incontinence because you don't have any micturition reflexes. It just drips out. Okay? They never know that they have to go, and they're going to have time actually voiding the bladder. Now, what if you damaged the spinal cord somewhere? And here it says above the sacral region. So it's above the sacral region, say lumbar, thoracic. You'll have micturition reflexes because it's mediated through the sacrospinal cord. So that's going to be going on. But the thing is, guess what's going on with that up above the sacrospinal cord? You had ascending information that came up and told you, hey, I got to go. So they don't know that they have to go, but the bladder's going to start to contract, and so they call it automatic bladder, and I call it pre-potty training bladder, because that's really what it is. So that's when they pee, and they didn't or aware of the fact that they peed. So the kid's has got his diaper on, and he's peeing along, thinking fine, everything's fine. You just pee. So if you damage the spinal cord, do you think this exists in real life? Do people have spinal cord injuries all the time? So just defecation could be issues. Micturition can be an issue. Okay, so that could be a problem. Now the last one, they call it interrupted neurogenic bladder, where somehow the inhibitory signals. So you have the sensory information that's coming up to the higher brain centers. I said you have higher brain centers that can kind of suppress the whole process, kind of tell the bladder to stop contracting. I said if you hold it, then sometimes you don't notice. Once you're, oh, don't really have to go as much. It kind of, the bladder wasn't contracting anymore. Well, if you interrupt those signals, they're sending down these inhibitory information to suppress what's going on there. What they have is like they're going to have to go, like feel like, oh, get a little bit of filling of the butt. Oh, gotta go. Gotta go. They feel like they have to go all the time. They can't spread. So it's time to go. They can't just hold off because they feel like they have to go all the time. So just a little bit of stretch, there's like, I gotta go. And some of this one not necessarily, I can give you an example of this one, is not necessarily permanent. None of these necessarily have to be permanent, because sometimes if you mess up with fibers, you can get recovery. I mean, you can kind of irritate something. So not necessarily everything's going to be irreversible, but you can get uninhibited neurogenic bladder sometimes if you've had surgery in that area, because they're messing around, moving things around, and kind of not damaging the nerves, but kind of messing with them. And they're like, so for a short period of time after they've done surgery, you may notice that, oh, I got to pee for no reason. That's what happened after my surgery. I had to pee before the surgery because of the pressure on the bladder, but then I removed it. I'm like, God, why do I have to pee so much? I thought taking this thing out wouldn't make me pee. Well, we were in there messing around, pulling things around. It says, you're going to have to pee a little bit more, but I can give you something for it. I said, no, is it going to go away? Okay. He said, yeah, it'll go away. I said, all right, I can make I'm smart enough to go to the bathroom when I need to go. I'll just go when it happens. So the messing with the area, it kind of aggravated it, so I had this neurogenic bladder just for a little bit, okay? So issues with bladder control become a problem as you get older, though, unfortunately, you know. And sometimes some of the women, if you've had a lot of children, there's like when you're or even girls that you don't have children, you always hear that if you're pregnant, you have to do Kegel exercises, things like to kind of stuff get weaker, and that you need to do Kegel exercises. They're not the pleasantest things to do. They're kind of hard to do. And it's like, gentlemen, well, I don't know if it's the same thing with the guys if you do it. You have to try to stop going to the bathroom midstream. Is that kind of hard to do? It's kind of hard. It's kind of hard, okay? It's kind of that. It's like you're trying to pull up your pelvic floor muscles, or it's kind of hard to do. And so sometimes those muscles don't kind of need to be worked out. And so it's harder to kind of hold things in. So you can become a little incontinent sometimes as you get older, okay? So unfortunately, yet another thing to look forward to, maybe. Hopefully not. All right. What? Paul? Or no, Paul, Peter. Peter, Paul. Where's Mary? Okay. All right, so let's just go backwards now. We're talking about peeing. We got to go talk about let's making the urine in the first place. So there's 3 basic things involved in urine formation. We're going to really talk about today the whole process of filtration. So you filter stuff. This arrow right here is representing glomerular filtration. So glomerular filtration is you're having fluid, electrolytes, all this stuff leaving the blood and entering the Bowman's capsule. That's filtration. Whatever is along the nephron tubule that's reabsorbed, it's going to go from the nephron tubule across the membrane, eventually in the interstitium, eventually into blood. That's reabsorption. So here, this arrow right here represents tubular reabsorption because it's taking place in the tubule. So if I want to recapture it, I better reabsorb it. There are some things that later on, if I want to get rid of, and it wasn't filtered, I can secrete it. So I can go from the blood through the interstitium into the nephron tubule. So there's some things that you can secrete that did not end up getting filtered. So the sum of what is filtered and secreted, and then whatever's removed, whatever's left, that's what you're going to excrete. That will be your urine. Okay, so it'll be excretion. If, yeah, Dallas.
Is that through those peritubular?
Yes. So the peritubular capillaries. So examples of 2 things that can be secreted. Hydrogen ions, potassium. So it'll be within peritubular capillaries. I can secrete it. It's going to go from the blood, and it's not in the glomerulus, from the peritubular capillaries into the nephron tubule. So some drugs can be secreted too. Some of the medications like penicillin, things like that can be secreted. So whatever is in the urine is your excretion. So that's very important to know the distinction between secretion and excretion. They're 2 different things. Okay, so something is secreted. Because don't I secrete like hormones into the bloodstream? Doesn't necessarily mean I'm excreting it. Something that's excreted, something that's you're going to get rid of from your body. Okay, so we're going to look at what is involved in this whole process of filtration. Next time we'll talk about reabsorption and secretion. So things that will be filtered. And then talk about, well, do we have it set up that we're going to reabsorb things or not so much? Nutrients like glucose and amino acids, they will be filtered. Do you want them to be excreted from your body? I just went through the hassle of breaking that stuff down, and I want to filter it through my kidneys and get rid of it. That's wasteful. But remember I said filtrations is relatively nonspecific. The good, the bad, and the ugly get out, but I want the good back. Okay? So nutrients are filtered, but they were designed to reabsorb them. If everything works out just right, all of the nutrients, and I'm talking glucose, amino acids, those will be completely reabsorbed. Okay, they should be completely reabsorbed. You filter things like electrolytes, sodium, potassium, chloride, all that stuff. Well, depends on what's going on. Most of it will be reabsorbed, but it depends. If I need to get rid of some extra sodium, I will. If I need to get rid of some extra potassium, I will. But one thing to remember, though, if I'm a substance that's filtered and I need to, like, I want to get rid of some extra, is I'll just not reabsorb it. But there are some things that can be secreted if I want to get rid of some extra, either not reabsorb it or secrete it. But not everything can be secreted. So just remember, if something is filtered and not reabsorbed, it's going to appear in your urine. So sometimes, generally, it's a matter of, do I reabsorb all of it or not as much of it? So then I'll leave some over in the urine. Metabolic waste, what do you think? Filtered? Yeah, isn't that the whole purpose of what the kidney's doing? Filter some metabolic waste. Do you think we have transporters that allow us to reabsorb those things? Do you think we got a lot of transporters that allow us to reabsorb metabolic waste? You would think not, right? So like, isn't that the whole purpose? I need to get the stuff out? Depends on the metabolic waste. That's where the tricky part is. So here's the tricky one. Creatinine. Creatinine, not creatine. Creatinine. That's the breakdown product of creatine. We don't have any transporters that allow us to reabsorb that. That's just going to be filtered and just end up in your urine. Okay? Breakdown product of muscle metabolism. Urea, isn't that like our major metabolic waste product most people think about? Urea? Do you remember that in biochemistry, doing the urea cycle? Yes, you do. Okay? Urea is filtered, but we reabsorb some of it. You're like, oh my, what? It's a waste product, but we're going to use it to our advantage. Trust me. We're going to manipulate it. We're going to use it because that's going to help us in the whole idea of water balance. But again, don't worry, we'll get rid of it. We're just going to use some of it, but we do actually reabsorb that. Not a heck of a lot, but enough that it's going to be significant. You're like, why do we reabsorb that? We use it. It all depends on what part of the tubule we're in, too. Foreign substances, drugs. Filtered them? Yeah, it depends on it. Are we going to reabsorb those things? Do you think our body has transporters long enough to, oh, I better get that penicillin back? No. So we don't have mechanisms to reabsorb them. Now, some drugs, if we don't filter all of it, we can secrete it later in different parts of the tubule, get rid of it. But this sometimes is a problem with certain medications where the clearance rate is so high, it's hard to get a or what's the term I want? That's what I want. The therapeutic level. So sometimes they have to, give you more and more to get, because you clear it so quickly. Like penicillin's an issue. Sometimes they give you some stuff to kind of so you don't clear it as much. So, but foreign substances, you want to get rid of them. That's the whole job. Get rid of the stuff that don't belong here. Let's get rid of it. Okay? So we're going to filter pretty much everything except, tell me again what things that we're not going to filter though. Or shouldn't. Well, we don't filter water? We're going to filter water, a whole mess of water coming out. But large proteins and blood cells. Water's coming out, trust me. Because don't you think, isn't there some water in our urine? But don't worry, we're going to get a lot of that back, okay? But we can change the amount of water in our urine, right? Can't we? Depending on, did you drink 2 gallons of water right before you came to class? Do you think your urine volume is going to be a little higher in about an hour or so? It can change. It can be real high, real low. All right, so 180 liters per day we filter. Our glomerular filtration rate, GFR. You can just use GFR. That's a lot. That's a bunch load. Okay, I was going to say something else, but it's a bunch load. Okay, it's a lot. Okay, so we pretty much can filter our blood volume quite a number of times a day because, again, its job is to get rid of waste products. But actually, it's like 22%, we said 22% of your cardiac output goes to the kidneys. That's a significant amount of blood flow to the kidneys, okay? Here's a number. There's not a lot of numbers in the renal phys part that I want you to remember, but this is one. 125 mils per minute is your GFR. It equates to about 108 liters, 80 liters a day. 125 mils per minute. That's pretty good. I'm going to show you how they came up with that number. So this is where it's a flashback from Physio 1. Ooh, okay, Starling forces. I'm just going to do it just to be mean, but I want to show you how the stuff applies. Now, the way it's set up, how this whole thing's designed, you've got those pores, those fenestrations, that allows the bigger, bigger things get through, but not too big. But also something to keep in mind is the way the Bowman's capsule is arranged and the glomerulus is, there is charges on that Bowman's capsule that tend to repel the larger negatively charged things. And what would be a larger negatively charged thing that try to kind of say, oh, you're not coming through? Proteins. So if somehow you damage that, though, that's where sometimes you can start getting these proteins that leak out. Okay, so you do have some protection there, prevents certain things from not leaving. But here's another thing. I said it earlier, but I'll say it again. You said proteins can't get out, large proteins, blood cells, but here's another one. Anything bound to a protein can't be filtered. And the one that I want you to remember, calcium. Can calcium be found in 3 different forms floating around in your bloodstream? And it would be yes. 3 ways that calcium hangs around in your bloodstream. Bound to plasma proteins, bound to anions, and what's the other way? What? Say it, Felipe. Well, that's anion. Okay, so anions. What's the one that's the hormonally regulated quantity of calcium? That's the one that we want to make sure is at adequate level. The free ionized calcium. Okay, so but the calcium that is bound to protein is not going to be filtered. Okay, but the ones that are free ionized can be filtered. And we'll go over that too. Like, how do we, remember, we're going to actually go back to parathyroid hormone a little bit later, not today. So we'll talk about some of the endocrine stuff a little bit. So here is where the Starling's forces come into play. I put the numbers in there. Don't memorize them, except maybe the 60 for the glomerular hydrostatic pressure. Let's just review real quickly these Starling's forces before we look at what's going on in the glomerulus. You have a blood vessel. This is my blood vessel going down the aisle, okay? We had hydrostatic forces and we have osmotic forces. I have them in the blood vessel, I have them in the interstitial fluid, okay? Remember, hydrostatic forces want to push fluid out, away from me. I should say away from me. Osmotic forces are drawing fluid towards me. So in your blood, you have a we're just going to use the general systemic circulation. Your capillary hydrostatic pressure. What's it wanting to do? Force fluid out. In the general systemic circulation, you said it's about 17.3. Notice glomerulus, how much higher it is, but it's important. So we said, oh, what's the reason why it's so high? Because having it set up in series, having the efferent a little bit smaller than the afferent, we want that really high pressure. So that's trying to force fluid out. But I have blood proteins, I have plasma proteins in the blood, creates a plasma colloidal osmotic pressure. And what's that doing? It's favoring not filtration, but absorption or reabsorption, depending on where we are, absorption, reabsorption. Okay? We still have that here, so that will oppose. So we're going to, in the kidneys, we're going to say, does it favor filtration or oppose it? Remember, we all want filtration. That's all we want there. Okay? Then I'm in the interstitium. There's a hydrostatic pressure in the interstitium. Remember that one was the variable one? It could be a positive number, it can be a negative number. Remember that one? That's the tricky one. But normally, if I have fluid in the interstitium, what's that wanting to do? I'm a hydrostatic pressure. I'm wanting to put fluid back into the capillary. That's if it's a positive number. I also may have proteins out here, and that's wanting to draw fluid out of the vessel. So you have things that are wanting to favor filtration, things that don't want to favor filtration. And we set up the math, we did all that fancy math, and in the end, figured out what do we get. Do we have a net filtration pressure or net absorption pressure? If you do it here, notice I have eliminated or have not included one pressure for a reason. The Bowman's capsule is going to be equivalent to our interstitial fluid for this one. Here's your glomerulus. We've got the pressures here. Bowman's capsule hydrostatic pressure, because you have fluid here, it's trying to force or oppose filtration. What pressure am I ignoring? And there's a reason why I'm ignoring it. I don't have an osmotic pressure there, but why? That should be 0. Why? Yeah, I shouldn't be filtering protein, so that's going to be 0. That's why I didn't even include it. If you want to put it there, just put a 0 in there. What you'll notice if you do the math, do all the fancy math, what you'll get is a net filtration pressure of 10 millimeters of mercury. Okay, yeah, so 10 millimeters of mercury. Do you remember when we did this, we talked about filtration coefficients? So if I know my net pressure difference, say the filtration coefficient says how much fluid is going to move across that membrane per minute for every millimeter of mercury pressure difference. So if you have your net filtration pressure here, 10, in your glomerulus, it has a filtration coefficient of 12.5 mils per minute per millimeter of mercury. So if you do the fancy math, and it's not that fancy, it's times 10, we can just move the decimal over. What is our GFR? 125 mils per minute. Isn't that what I just told you earlier? I just showed you how I got to it. So it's pretty high, mainly because of the glomerular hydrostatic pressure being that high. But just like anything else, could we affect that filtration, that GFR, if I messed with any of those values? Could I do it? I could. I'm going to do it. So what would happen to your GFR if this pressure dropped? What could happen to your filtration? It could decrease. Does the kidney like that? Is the kidney going to like it? Mm-mm. And we're going to talk about how it's going to say, no, don't like it. I'm going to have to do something to get that pressure back up. Don't like it, but it could decrease filtration. What about this pressure here, Bowman's capsule hydrostatic pressure? You'll do a little mock of something like this in the lab, or you'll talk about it in lab. If that pressure increases, what will happen to filtration? If Bowman's capsule hydrostatic pressure, it's like pushing up here. What's it going to do to filtration? Is it going to favor it or oppose it? Oppose it. You know what can cause that to go up? If you got a blockage, got a stone, that block maybe even a ureter, pressure, everything starts to back up. That pressure can increase. But think about it, it's like pressure's going to increase. Kind of your body's innate. That increases is going to pose more filtration. So like, I have nowhere to go. Stop producing pee. But it's like, actually, it's not necessarily a good thing. But it will try to oppose filtration. So if you have some sort of stone that's blocking it, that can increase that pressure and decrease your filtration. So different things can affect the glomerular filtration rate. But what we're going to be talking about is, remember, kidneys better have an adequate one. My job to get rid of filter, to get rid of waste products. So it's going to do what it needs to do to keep an adequate filtration. And generally how it's going to do it is make sure that this pressure is high enough. And the way I'll do it is by affecting the diameters of those afferent and efferent arterioles. So you have a table in your notes of things that can influence GFR, and a lot of them are just more pathologic. So these ones are like considered more pathologic. So if I decrease the filtration coefficient, which can happen if I damage blood vessels or I damage the filtration membrane. You've got diabetes mellitus that can create problems. High blood pressure, kidney disease. That's all pathologic. I just talked about the kidney stones. Those things can do it. These are the ones that I want to really talk about, the physiologic things that can affect filtration. Now this one, This isn't going to be a huge factor because we're going to review, and I did say review, autoregulation. Okay, so we're going to look at autoregulation. If you affect your mean arterial pressure, your arterial blood pressure, that could affect it because that would affect glomerular pressure. But because of this autoregulation that takes place in the kidney, it's not going to have huge dramatic effects because it's trying to make sure it keeps the GFR pretty much stable. Doesn't want it too high, doesn't want it too low. Here, these two, if you change the diameter of your arterioles, they can affect, and we only have you one scenario, things that would, I think, would decrease GFR, but the opposite would increase it. So I had mentioned it a little bit earlier. So let's kind of envision it again. So I have, here is my afferent arteriole. Here's my efferent. We're going to say it's a little bit smaller. Here's my glomerulus in the middle. Okay? So because of that being smaller, it kind of helps increase the pressure so it kind of comes out. So if I make the afferent arteriole bigger, what's that doing? Is that bringing more or less blood into the glomerulus? If I make the afferent arteriole bigger? More. Would that favor filtration? Yes. That's one way I can do it. So if I increase the diameter of the afferent arteriole, or I could say it a different way, what would I say to resistance? What would I do to the resistance of the afferent arteriole? Decrease the resistance. That could increase filtration. The opposite would decrease it. If I decrease the diameter of the afferent arteriole, I'm going to decrease GFR. Okay? The other one, the efferent, if I decrease the diameter, that could increase filtration because it's going to provide more back pressure to a certain extent. You don't want it too much because then you're going to affect total blood flow. But to a small extent, if you decrease it, that could increase filtration. If I dilate the efferent arteriole, I open that thing up, I don't have that back pressure anymore. Your filtration will go down by changing. You're going to have a little thing. Have you guys done that in lab yet? Or is it this? Did you do it? People had Monday lab? So you did the little PhysioX thing where you messed with the diameters of afferent, and you kept watching to see what happened to GFR? Yeah. If you mess with the diameters of them, that's how you can affect GFR. And that's how we physiologically do it. The certain hormones, certain effects of the sympathetics could affect what's happening on there. Angiotensin II is going to be a very important player in this whole regulation of the diameter, specifically of the efferent arteriole. Have we talked about angiotensin II before at some point in time? I think I have, but I'm going to talk about it again a lot. Okay, so angiotensin II is going to be very important, and it is a hormone that's going to control what's going on with kidney function. So it does things in regards to aldosterone. Do you remember how it played a role with aldosterone? Because that's when we talked about this try. We'll talk about what it does in the kidney. So we'll look at those at a little bit later. So they can influence your filtration rate. Now let's just do a little side thing about blood flow. I'm not going to spend a huge amount of time. Remember we talked about local control of blood flow? Do you remember local control of blood flow lecture? I just did that lecture today in Physio 1. It's fresh in my mind, okay? Local, remember talking about vasodilator theory, oxygen demand theory. Sound any kind of familiar at all? No, nah, whatever. Okay, no. Had a table, and I said, oh, certain circulations in our body are controlled metabolically, some by function. Say skeletal muscle, is it controlled metabolically or by function? Metabolically. More active? Going to need more blood flow. Okay? So skeletal muscle is metabolically controlled, brain is metabolically controlled, heart's metabolically controlled. Skin, functionally, it's all about temperature regulation. The hypothalamus determines if you're getting your blood flow or not. I don't care what's going on. If you're getting too hot or not, it's going to control this. It doesn't care what's going on with the skin. It's just about changing your body temperature. Lungs, functionally controlled. Kidneys, it's all about function. It is not a metabolically controlled circulation. Okay? even though it's get a huge amount of blood flow, it's there just to have for filtration. And what we're going to look at is we say, well, it has a high demand for oxygen. You know, like a lot of oxygen goes to the kidneys, and it's not really necessarily linked to metabolism. It's because why do we need so much oxygen in the kidneys? It actually gets more oxygen than it really needs. Think about what do we need oxygen for? I don't even bother to show you the picture because it can confuse students. What do we need oxygen for? Well, we're breathing to get the oxygen, okay? Electron transport chain to make some ATP. Okay, so you need it to make ATP. Why does the kidney need so much ATP? What's it going to be doing? It's going to be transporting a lot of stuff because we're going to be filtering a whole bunch of stuff, but remember, we need to get all the good stuff back. And you notice they're going to need a lot of energy, a lot of ATP consumption to reabsorb things like sodium, and then a lot of other things come along with sodium. So there's a lot of energy involved in just reabsorption of all these different electrolytes and nutrients. So its job is, okay, I'm filtering all this stuff, but I'm going to recapture the new stuff. So it's functionally controlled. It's not metabolically controlled, even though it does get a fair amount of blood flow. But it stays pretty much constant. We don't want too much. We don't want too little. Just right. So I'm going to skip through here so you don't. I'm going to skip that too. All right, so we're going to go to this thing. There is differences in the amount of blood flow in different parts of your kidney. One of them you could answer. One of them you probably won't be able to answer. Most amount of blood is in the cortex. Wonder why. What's going on in the cortex? That's why it has the most amount of blood. That's where your filtration's taking place. Got all that filtration. Most of the parts of the nephron tubule are located in the cortex, so we're going to get a lot of reabsorption going on there. That gets more of the blood. Not as much to the medulla. So, reason why it doesn't get a lot of flow, the flow rate's not as high, is it's going to be the renal medulla is going to be very important in regulation of water balance. And when we do that lecture, I'm going to show you about the vasa recta, how that's designed, how they're arranged relative to the nephron tubule. Their job, just like any other capillary, is, hey, I'm going to give you some oxygen. I'm going to bring up some waste products. You know, I'll give you some nutrients and things like that. That's its job, just like anything else. But it does not want to pick up things that it shouldn't pick up. And there's going to be some stuff hanging out in the renal medulla that may be very important when we talk of regulation of water balance. There's going to be stuff in the interstitium that I want to keep there because I want to draw water under certain conditions. So we're going to talk about urea. Ooh, waste product might be hanging out there. Some sodium might be hanging out there. That'll be important a little bit later. So I just want enough blood flow that I just keep you happy, but not too much I'm washing this stuff away. So that's where it's going to be important. So we don't want a lot of it there because it's going to be important in water balance. So let's talk about a little autoregulation. And we'll stop. We'll do the hormone stuff next time. So we'll just do a little autoregulation right now. What does autoregulation literally mean? What does it mean? Self-regulation. So the renal circulation is highly autoregulated. We talked about it last trimester. I'm going to talk about it now. You'll notice, despite a fairly large range in your blood pressure, the blood flow in the kidneys stay relatively constant as well as the GFR. So, here I just drew a flat line. Look at renal blood flow, GFR. Pretty wide range in blood pressures. That's pretty cool. But if you know the flow equation, you're like, wait, something's not right. According to the flow equation, Q equals delta P over R. If I increase your pressure, what should happen to flow? If I increase pressure, flow should go up. Look, it's staying the same. If my pressure drops, what should happen to flow? It should go down. Oh, no, staying the same. So something is going on that despite this pretty wide range in blood pressures, renal blood flow in GFR is staying relatively constant. Now you'll notice I drew up on the top this big circle and a small circle. Why am I putting a big circle and a small circle? So what has happened up here? What am I trying to depict here? The diameter of like a vessel. It's like, ooh, even though you think blood flow should go up, ooh, do it so that if I decrease something, blood flow will go down. The other one is like if I decrease pressure, say flow should go down. But if I open up a vessel, flow will go up. I'm trying to keep it constant. So what is it about the kidneys that allows it to auto-regulate? So it has a lot of things in place that allows that flow to stay relatively constant despite a change in blood pressure. Because it says I need an adequate filtration rate to get rid of waste products. But I don't want it too high. If pressures get too high, guess what? You could damage the kidneys, and that wouldn't be so good. So we want it just right. Keep the flow about the same. Okay? So there's this thing called the tubular glomerular feedback theory. So it involves the tubule and the glomerulus. So here is more anatomically correct drawn. Here's the afferent arteriole, efferent. Here's the early distal tubule. I said early distal tubule is actually in contact with those vessels. Here's those macula densa cells. These cells are chemoreceptors. What is a chemoreceptor? The sensory receptor that's sensing what? Chemicals, something. In this case, it's going to be sodium. It's a sodium sensor. So let's see what's going on. We're going to go through a scenario. But before we do that, let's talk about these juxtaglomerular cells. Juxtaglomerular cells are found along the afferent and efferent arteriole. Those are smooth muscle cells. They're actually baroreceptors. And what does a baroreceptor do? It's a sensory receptor that senses pressure. Okay? So they're really pressure receptors. So something's going to be linked to these pressure receptors, and what's also going to happen with the macula densa cells. So here's one theory of what's going on. So we'll go through a scenario. We can do the opposite. You just flip the arrows. We're going to say your blood pressure dropped. Your mean arterial pressure dropped. All right? What will happen to that glomerular hydrostatic pressure? Will it be 60? No, it's going to be less. Does the kidneys like that? The kidneys like, hey, wait, don't like it. Something's not right. I'm not going to be able to filter like I should. So this pressure drops, your filtration rate's going to drop. And what's going to happen? You're filtering less, and this is a rate. Remember, it's a rate, time, volume per unit time. When you're filtering, eventually it's going to go into the Bowman's capsule and then the proximal tube make its way. If you give it enough time, if I'm just moving on through, I'll have plenty of time to reabsorb stuff. Okay? If filtration's going too fast, maybe I'll have time to reabsorb the things that I need to. So my filtration rate has dropped. As I'm moving through the proximal tubule, guess what I have time to do? Because it's the rate. It's not going by too quickly. What am I going to be able to reabsorb? Stuff, and specifically sodium. Okay, sodium chloride. Sodium is the big one. Okay, so your reabsorption of sodium chloride in the proximal tubule increases. So where does it go from there? You got proximal tubule, the loop of Henle, and then when it made its way up, where do we go? Early distal tubule. And what cells are in the early distal tubule? Macula densa cells. So if you increase the reabsorption of sodium chloride, what happens to the sodium chloride concentration in the macula densa? They're going to decrease. And the macula densa says, hey, the amount of sodium in here is not quite as much as it normally would be. And so what does it do is it communicates. Again, I don't know the exact mechanism. No one does. The macula densa cells communicate with the juxtaglomerular cells. They talk. They have paracontract factors. It says, ooh, the sodium chloride levels are a little lower than they normally should be. Maybe that means that filtration's not adequate. So you need to do something to get filtration adequate. So it talks to the juxtaglomerular cells, and guess what the juxtaglomerular cells make? An enzyme called renin. And so what happens is renin is going to be secreted into the bloodstream. And this is by these cells right here. What does renin do? It's more than one step here. We've just jumped the gun. Renin causes a conversion, and it's not this directly here, angiotensin II. Renin converts angiotensinogen into angiotensin 1. Angiotensin 1 is then converted to angiotensin 2 by ACE, angiotensin converting enzyme. But the higher amounts of renin you have in your blood, you're going to have more angiotensin 2. So I got more angiotensin 2 around. Angiotensin 2 does a lot of things, but one of the things it does is a very potent vasoconstrictor, and it loves the efferent arteriole. Preferential is like, oh, they're like peas and carrots. Okay, so that's the Forrest Gump flashback there. So efferent arteriole, it constricts it. So what do I put there for resistance? If I say it's a constrictor, what happens to the resistance? Goes up. Okay, so if that increases, what do we say? What happens to your filtration? So remember, if I decrease the diameter of the efferent arteriole, it provides more back pressure, and that's going to allow filtration to go up. Okay, so that's one way, but the angiotensin does some other stuff too. Should we review what angiotensin 2 also does? So if your blood pressure dropped, how would angiotensin 2 help to get your blood pressure up, besides doing what it's doing in the kidney? It increases the formation of aldosterone. Aldosterone allows you to reabsorb more sodium, more fluid, tries to get your blood volume up. That helps to get blood pressure up. Plus, being a vasoconstrictor, that would help get your blood pressure up. But here it's just all about me. I want to get my filtration up so I have adequate getting rid of some waste products. Simultaneously, again, I don't know the exact mechanism for this one. What do you think should happen to the afferent arterial resistance? That should decrease. That will help to, excuse me, get the glomerular hydrostatic back up, pressure back up, to increase filtration. Okay? We can do the other scenario. If your blood pressure went too high, we can just flip every arrow. We could do it. And let's just do it. And let's talk about the significance of it. So if your blood pressure increases, so we're going to kind of talk about the role of the kidneys in blood pressure regulation. That's what I'm really doing, is reviewing you about that. My blood pressure is high. What's the role? How do the kidneys get your blood pressure back down? Well, pressure's up, glomerular hydrostatic pressure goes up. What happens to GFR? Goes up. You're like, oh, don't want that too high. So we can say, what's going to happen to the sodium chloride reabsorption? It's good. You're moving things a little bit too quick, and so you're not going to be able to reabsorb as much sodium, maybe chloride, but also not as much water. And so what happens, how do we get our blood pressure back down? How do the kidneys get your blood pressure back down? What happens to your urine volume? It increases. So you end up with pressure diuresis, as well as, because of the sodium, pressure natriuresis. And that helps get your blood pressure back down. That's how the kidneys work. And so what's going on with the levels of renin and angiotensin 2? Are they going to be high or low? They're going to be low. Okay? So they're all kind of linked in there somehow. So what about if I gave you angiotensin 2 blocker? What would that do? Its use actually decreases people's blood pressure. Okay, some people, that's one of the things they take, is to decrease their blood pressure. They give them angiotensin 2 blockers, receptor blockers. You can give someone a lot of different things to mess with their blood pressure, and that's just one of them. Okay? All right. So we're just going to stop there to give you guys a little break, because you're already learning mentally out of it. Okay? We'll talk about some of the hormones next time, then we'll go on to the stuff that's going on in the tubule, okay? The events that take place in the tubule. Oh, I forgot to set the roller on the second hour, so I guess I can't do that.